Do it again. Good morning, everyone. Is it better? My name is Chrystelle, and today I will present you some work I did during my postdoc in Strasbourg with Yves on the large strain modeling on polymer material and how they will behave. So no, in fact, I'm not in Strasbourg anymore. I'm in Tohoku University. So Tohoku University is located in Japan, in Sendai, in fact, which is 300 kilometers north of Tokyo. And it was founded in 1907 as the third Imperial University of Japan. And today it's the first engineering school in Japan, and with excellence in material science, physics, engineering, and technology. So today, one of the material I use is ultra-high molecular weight polyethylene, which is a petroleum-based polymer, but is also a very interesting property for biocompatibility, as it also have excellent wear and impact resistance, which make it a very good material for hip prostheses or knee prostheses also. And of course, it's not the only biocompatible material. There is also biomaterial, which come from biodegradable and biocompatible materials, such as PDMS that Professor Barakat, of course, showed us yesterday. So here you can see some PDMS which was molded in substrate in a collaborative work between Tehran and Strasbourg, and in fact the pattern is around 50 micrometers. And this kind of polymers are very used for contact lenses, catheter, and so on. And there is also other kind of biopolymers, such as PCl, PLA, and PVA, which can also be used for bio application. And here you can see some patterns which are around 50 micrometers also, I think, which were obtained by lithography and etching. But in fact, all these polymers, of course, have a mechanical behavior, and the modeling of this kind of material at very large strain is still difficult, even so, since past century, a lot of models have been developed. So today I will present you some work which was done in Strasbourg in previous PhD of mine. And in fact, here you can see the strain-strain behavior of amorphous polymer and its numerical modeling. So in fact, you can see that the numerical modeling fit quite well the experimental result, even at very large strain, since here we are at 120% deformation. But when we check what happened in shear behavior, you can see large discrepancy between shear loading and the numerical prediction. And this starts up to 20% deformation. So from 20% deformation, the discrepancy increases and just continue increasing. So why do we have such difference of behavior between uniaxial compression and shear loading? One of the first reasons is that the model is identified using uniaxial compression or tensile test. So of course, it will model quite well this behavior. But in that case, what is missing in our constitutive equation to be able to predict accurately the shear modeling, the shear loading? So one answer to this question is the following. So at small strain, it exists a linear deformation strain tensor, such as the time derivative of the strain function is equal to the rate of deformation tensor. But in fact, this is not true anymore in large strain, where the rate of deformation tensor is different from the time derivative of the strain function. So since the middle of 1950, large number of researchers tried to establish relationship between D, so the rate of deformation tensor, and the time derivative of the logarithmic strain function. And I will just present today one theory about it, which was developed by Roger in 1997, and which can predict well this behavior. And I have to say also that these different researchers developed more or less complicated relationships. And the one of Roger is one of the, let's say, simplest. So before going to the mathematical development, I will just present the rheological and model for the amorphous polymer behavior, which is quite common. So here we have a linear spring in series with a dashpot in parallel with a Langevin spring. So the linear springs is modeled by the Hooke's law with the logarithmic strain function. And the Langevin spring is here to model the large strain behavior of the polymer. So when we have the orientation and hardening of the polymeric chain. So the polymer behavior is doing something like this. And the backstress tensor here is here to represent this hardening here. And the dashpot that I will not elaborate today is based by is modeled using the cooperative model, which is strain rate and temperature dependent. So just a small remembering of the kinetics. So we decompose the deformation gradient into elastic, thermal, and viscoplastic parts. The elastic behavior is given by the Cauchy stress tensor with here the logarithmic strain function, and the backstress tensor is given here by the A-chain model, which have here the deformation difference or Green-Lagrange strain measure. So if we check what happened for the logarithmic strain function, we define some simple definition here with u equal to delta lambda I delta I minus 1. So delta, in fact, is the eigenvalues. And we define also the spin tensor here, such as here. And when we play with our equation, so we will have the time derivative of the logarithmic strain function, which is given here, with difference between A equal G and A different from J. And the rate of deformation tensor is given by this equation here. So you can see that for A equal G, the equation is the same, but here for A different from G, equation is a bit different. And to link time derivative of U with D, we'll have to use the spin tensor here. So when we use correlate with the spin tensor, we obtain the following equation. So ln du equal kd, with k defined here. So for this to be accurate and to stay accurate with the law of mechanics, we need also to check if it satisfies the power density of internal forces. And when we do that and we replace d by its value given previously, we see that we need to update the Cauchy stress tensor, and therefore we got this equation for the Cauchy stress tensor for the associated to the logarithmic strain function. As I showed you previously in our model, we have two different strain measures. One is a logarithmic strain function. The other one is the Green-Lagrange strain measure. And so we did the same as we did here, and which was demonstrated by Roger in 1997. And we got the following for the time derivative of the deformation difference strain measure. Of course, the rate of deformation tensor stays the same. And we obtain quite simple time derivative strain function equal to the rate of deformation tensor here. And so we do the same. We update the backstress tensor, and we find this kind of equation for the backstress tensor. So know what happened to the prediction of the mechanical behavior. So if we look at this result here, when we take into account the elastic and viscoplastic transport, here you can see that the curve in black corresponds to the model I just explained using the same parameter as the one were defined previously in the first model. And we can see that it becomes kind of out of range, and therefore it's needed to re-identify the model parameter to fit accurately the experimental results. So by re-identification of the parameter, we can fit quite well the uniaxial compression. And if we check at what happened in that case in the shear loading, we can see here a highly improved prediction of the shear loading behavior compared to what was done previously. So we were kind of very happy with that. So for conclusion, I will say that our large strain, it doesn't exist any relationship a priori between the rate of deformation tensor and the time derivative of the strain measure. So it's needed to take into account more assumption, more movement to have this kind of equation which is verified. And by doing this, we also increase the number of operations kind of a lot, but we are able to predict accurately the deformation in both compression and shear loading. And with the cooperative model, we have also the strain rate and temperature dependence we play. And if you are interested, we published this last year in M&MoCS, so you can refer to the paper. Thank you very much for your attention.